A small rocket is fired from the ground at an angle of theta degrees to the horizontal with a speed of 70 meters per second. The rocket has the assistance of a steady wind that is blowing horizontally at W meters per second. A coordinate system is set up to track the path of the rocket as shown below. So we don't need to worry too much about this stuff just at the moment. But if we think about the initial velocity, so that is 70, and this angle is theta. So resolving, in other words using trigonometry, this one is the adjacent, so therefore we've got 70 cos theta that way, and this one up here would be the opposite to theta, and therefore that's 70 sine theta in that direction. Okay, so the acceleration is 0, negative 0.8. So we want to get the velocity, and we do that by integration. So in the top, we're just going to get a constant, which I'll call C1. In the bottom, we'll get negative 9.8t plus a constant. So we know that V is equal to, V is equal to 70 cos theta and 70 sine theta when t is equal to 0. So our velocity vector would be 70 cos theta and 70 sine theta, take away 9.8t. But we also need to take into account that there is a helping wind. So we need to add that in to the horizontal component. Now to get to r, we just need to integrate again. So we're going to get 70 cos theta plus w times t here, and on the bottom we'll get 70 sine theta times t, take away 4.9 t squared, and of course once again we need constants. But we know that r is equal to 0, 0 when t equals 0, and that tells us that C3 and C4 are equal to 0, and that gives us the r that we've got here, which is 70 cos theta plus wt and 70 sine theta t, take away 4.9 t squared. So we want to obtain the Cartesian equation for the path of the rocket in terms of theta and w. Well, x is going to be 70 cos theta plus w t, and y is going to be 70 sine theta t, take 4.9 t squared. For the Cartesian, what we need to do is get rid of t. So t is equal to x over 70 cos theta plus w. So y is going to be 70 sine theta times x over 70 cos theta plus w, take away 4.9 times x over 70 cos theta plus w squared. Let's just tidy that. So we'll put 70 sine theta x over 70 cos theta plus w. Take away 4.9 x squared over 70 cos theta plus w, all squared. The range of the rocket is defined as the horizontal distance travelled from the launch to where it starts the ground. Assuming that the wind speed w is 2 meters per second, determine the optimum angle theta so that the range of the rocket is maximized. Correct to the nearest 0.1 degree. So it's going to hit the ground when y equals 0. And so x equals 0 is one possible solution to that. And the other solution is when 70 sine theta over 70 cos theta plus 2, remember we were told to take w equals 2, take away 4.9x. So I've eliminated the x equals 0, so now I can divide through it by an x, over 70 cos theta plus 2 squared equals 0. So the solution to this will give us the other value of x. So 4.9x over 70 cos theta plus 2 squared would be equal to 70 sine theta over 70 cos theta plus 2. So that gives me that x is equal to 70 sine theta, 70 cos theta plus 2 squared over 4.9, 70 cos theta plus 2. And one of those will cancel with one of those. So x is going to be 70 sine theta times 70 cos theta plus 2 over 4.9. So we actually want to find the maximum of that. So I've actually graphed the function and I changed into radian mode, and I had to play with the window a bit. I've made the y from 0 to 1000, but basically we want where that maximum is, just there. So I'm going to go analysis, gsolve, and a max, and that's 0.795 for radians. And they probably want the answer in degrees, which they do. So let's go back to main, and I'll just clear all the rubbish that's on the screen. And so 0.7954, let's multiply that by 180 and divide by pi, and that's 45.6 degrees.